Okay, so why do we learn all this stuff about waves? I mean, after all, it technically falls into the physics category, but the reason we did is because waves and electrons have a lot in common, and electrons technically fall in the chemistry range. So electromagnetic radiation, all those waves that we saw, are created by exciting electrons in an atom. And so what happens is, this is the typical Bohr model. If you have an electron, okay, and you zap that electron with some electricity, like in a neon light or whatever, what will happen is the electron will jump up. And it might jump up from energy level 1 to energy level 2, or to level 3, or all the way up to level 4, or even beyond. And that's called being excited. It's an excited electron. So I add electricity to it, it jumps up, it absorbs the energy. This is an endothermic process, and it absorbs a certain amount of energy. So energy goes in. And then when it relaxes, when it drops back down, energy goes out in the form of light. And every element has a different amount of light, a different energy of light come out. So each element has a unique transition for its electrons, and that's where we come up with this whole idea. So the energy comes in, excites the electron to a higher energy level, it gets excited, it absorbs the energy. The same amount of energy is released in the form of light when the electron drops back down, and the electrons can move between the energy levels, and the farther they go, so this one was 2 to 3, if it went from 1 all the way up to 4 and then dropped all the way back down, it gives off a lot more energy when it makes that transition, or if it goes out to 5 or 6 or 7 or 8. And the farther it moves, the higher the energy of the light released. And from that we can calculate, based on what we know about E equals HF. We know the frequency, we can calculate the energy, and we can calculate the energy of that transition, and every transition is unique for every element. So what it looks like, you've got your energy level, okay, it releases a photon of light, and it's a relaxed electron. It gets excited from energy, and when it releases light in a specific wavelength or a specific frequency. So red light is less energy because it's a shorter transition. Blue light is a bigger energy because it's a bigger transition. So what does electromagnetic radiation have to do with electrons? Well, this is where Bohr came up with his model. He found that when electrons or elements are excited, all right, you add electricity to them, each element produces a unique color. Thus, a wavelength and energy of each transition is unique, and it's called an emission spectrum. It's different from a continuous spectrum. He theorized that when the electrons release light as they move, they're only allowed to move certain distances within an atom, and it's referred to as a quantized energy level. So their energy levels are allowed to transition between the levels, but in between the levels. So it's like an elevator in a hotel, right? You can get off at the first floor, the second floor, the third floor, but you can't get off at floor 2.75. Okay, you're only allowed to get off in certain distances. This is what a rainbow looks like. This is what, if you put white light through a prism, you'll see a continuous spectrum. If you do something like neon or something like the stuff we're going to do in the lab, what you see is you only see certain lines. And what that tells you, each one of these has a unique amount of energy. Blue line has the most and red line has the least. And each one of those transitions corresponds to a different transition for that electron back down. And the farther away it is, the more likely it is to be in the blue spectrum. So this is just to give you an idea. Here's a rainbow, okay, white light, and then mercury, lithium, all these different elements. If you notice, they're all kind of different. They all have different energy transitions for their electrons. And with hydrogen, hydrogen's the one that Bohr really studied. The visible series drops down from higher energy levels down to energy level 2. And then there's a couple other series. Infrared drops from higher levels down to level 3. And ultraviolet, because that's even higher energy than blue, is from higher levels all the way down to 1, very close to the nucleus. And those transitions are the most energy ones we have for hydrogen. So Bohr was right about that, but he was also kind of wrong. His model works great for hydrogen. It works not so great for anything with more than one electron. So he came up with some ideas, but he couldn't run the mathematics. He couldn't do the mathematics. And so there was another guy named Schrodinger. You've probably heard of Schrodinger's cat. Same guy, different idea. But the idea is he came up with this mathematical model for an atomic orbital. And it's a region of space in which there's a high probability of finding an electron. We can't really know where they are. That's something called the Heisenberg uncertainty principle. But there's a good chance of finding them. And the bigger the energy level it is, in other words, the farther that circle is out, the more energy level, the more orbitals there are in a given energy level. So like I said, this is like a hotel. And on the first floor, it's only got one room because it's such a small floor. It doesn't have a room for a whole lot of places. And then the second floor is a little bit bigger, and we have room in there for 3 rooms. When you get to the third floor, there's enough room in there for 9 rooms. And then you get to the fourth floor, there's 16. Fifth floor, there's 25. You might see a relationship there. So each orbital is given a specific unique quantum number. It's like an address. And we're going to go through those a little bit. So the relationship between energy levels and orbitals. Electron has a -1 charge. It is in the electron crowd surrounding the nucleus. And he thought they were in energy levels. That's where we get these circles from. Technically, they're not. Okay, technically they're in areas of space. They're regions of space around the nucleus. So they're a high probability of finding the electrons. Each energy level has at least one orbital, and that's where the electrons are, the regions of space where you can find them. Energy level 1, that'd be the first circle, is closest to the nucleus, so it's the smallest in size, and it only has one orbital, and it's called the 1s orbital. So, the orbital is the 1s, shaped like a sphere. This is what it looks like. So the electron is bouncing around in here somewhere. Okay? Once you get to energy level 2, so this is energy level 2. It's a little bit larger in size than 1. Now we've got a total of 4 orbitals. And here's the weird thing. One of them is a 2s orbital. It's that sphere, only it's bigger than the 1s. And then there are 3 other ones that are identical except for their orientation in 3D space. As a group, they're referred to as the 2p orbitals, but there are 3 of them, but we call them by their group name. Okay, and they're shaped more like dumbbells or peanuts, so this is what they look like. So this is a p orbital, this is a p orbital, and this is a p orbital. So that's what it looks like. Down there in the very center is the nucleus, then you got the 1s, and then the 2s around that, and now you got the 2p. Okay, energy level 3, this would be the third circle out. There are a total of 9 orbitals. The smallest one, or the lowest energy one, is a 3s, again, a sphere. Then there are 3 of those identical orbitals that are called 3p, p meaning they're shaped like a dumbbell, and they have different orientations in space. So that adds up to 4 of them so far. We've got a total of 9. The last 5 are referred to as d orbitals. And again, there's 5 of them, and they're shaped more like floor-leaf clovers, except this one, which is weird. So this is what they look like. So in the center of your atom, this is what you've got, okay? You've got way down in the dead center, you've got your nucleus. Then you've got the 1s and the 2s, and then all the 2p's, which look like these green and yellow and blue ones. And then you've got your 3s, which is a little bigger, and then you've got your 3p's, and then you've got your 3d's. This yellow one is one of them. That's the donut one. And so they're all kind of surrounding the nucleus. Once you get to energy level 4, that'd be the 4th energy level, 4th circle out. It has a total of 16 orbitals, and the lowest energy is called the 4s. And there are 3 identical ones called the 4p. We've seen those before. There are 5 called the 4d, so you might notice 1, 3, 5. Adds up so far to 9. We've got 16 to go. That means the last 7 are referred to as f orbitals. Okay, and S, P, D, and F, those letters are not chosen randomly. They stand for sharp, prime, diffuse, and fundamental, which are the 4 lines for the hydrogen spectrum. That's where they got the names from it. But S, P, D, and F, those are the 4 orbitals in the energy level 4, and these look really bizarre, okay, kind of all over the place. And that's what they look like when they're all put together. And again, dead center is the nucleus, and then you got everything else on the inside. And those are areas of space where it's likely to find an electron. So, are there other energy levels? Absolutely. They go on up to infinity, farther and farther away from the nucleus. Now, as you get farther and farther away, the distance between them gets smaller every time. And so I can't really draw that very well. So like, here's energy level 1, here's energy level 2, and energy level 3 is a little bit closer. And then energy level 4 is a little bit closer than that. And it keeps going like that. So it keeps getting, they're concentric circles, but they keep getting bigger, or the distance between each concentric circle gets smaller every time. And we're not going to worry about going beyond 7. So each increase in n, that would be these circles, leads to additional orbitals. And each orbital is capable of holding 2 electrons maximum. We'll get to that when we start talking about electron configuration. So in the first circle, there's only one orbital. It's called the 1s. There's only one of them. It holds 2 electrons. In energy level 2, that's the second circle, there are a total of 4 orbitals. There is 1 called a 2s and 3 called a 2p. Total number of electrons, 2 and 6, for a grand total of 8 in energy level 2. Third circle out, we got 9. We got these guys. Total number of electrons is 18 in that energy level. Level 4. Fourth circle out again. And now you're up to a total of 32 electrons. And when you get to the 5th energy level, 25 orbitals, S, P, D, F, and then after this they start to go alphabetical, but you'll never use anything in this guy. Anyhow, same idea, they line up, how many electrons, and total is 50. So using these energy levels and these orbitals, we can account for where all the electrons are. And the whole idea behind it is electrons behave like waves. They produce light when they make a transition. And that's where we get the idea for using the wave calculations to show you how waves have energy and how that relates to electrons.